Practice question set number 29. Quite a few questions on this one. We start with some information here in this box. It talks about artificial transmutation. We know what that means, right? Not radioactivity. Artificial transmutation is something that we make happen versus the natural process, the random process of radioactivity. But in the end, the way we do a transmutation equation is exactly the same whether it's natural or artificial. Doesn't make any difference here. The question, we'll just skip right down to the question here. It says the new unstable nucleus formed in the artificial transmutation is what? Well, it does say that beryllium-9, that means that it's the mass number 9. How do we know the atomic number for beryllium? I don't remember it. Check your periodic table. Okay, I had to look it up when I did the answer key to this. Beryllium-9 has an atomic number of 4. That means 4 protons, 5 neutrons. It's struck by an alpha particle. So we're going to put the alpha particle on the left-hand side. Now, usually we see the alpha particle on the right side, right? That's because it's alpha decay, usually. This is not alpha decay. Alpha decay has alpha on the right-hand side, but it's struck by alpha, then alpha is going to go on the left-hand side. What does it form here? Well, 9 plus 4 is 13. 4 plus 2 is 6. So we look on our atomic or on our periodic table for atomic number 6. This one I do happen to remember because it's very common, but you don't have to. Okay, we find that it's carbon. So the answer is going to be either C or D. Now, this is a bit tricky, this next part of it. The physics principle used to determine the atomic number for the stable isotope is conservation of what? If you check the bottom left-hand corner of your data sheet, it lists 10 different physics principles. And we've seen all of these, but we've done a handful of questions this year that have asked you about a physics principle. We're going to spend a couple days before the end of class. We're going to spend a little bit of time just going through all 10 of those physics principles, just to make sure that you know what each of them mean, okay? We're going to use one of them here. Is it conservation of nucleons or conservation of charge? Remember the other day we said a nucleon is a proton or a neutron. So in order to identify the atomic number, are we making sure that the number of protons and neutrons are conserved? Or are we making sure the total charge is conserved? It's charge. Yeah, it's charge. The answer is D. Okay, conservation of nucleons would be making sure that the 9 and the 4 balance to be 13. Conservation of charge, which is effectively the atomic number, we have to make sure that the 4 and the 2 balance out with a 6. That make sense? So nucleons, protons, and neutrons is balancing the top. Conservation of charge on the bottom. Like sometimes we might want to say conservation of protons on the bottom, but you know that sometimes we can have that beta particle, right, which is a -1. So really what you're doing is balancing the charge on the bottom there. The answer is D. 2, like this question. I'm going to give you the answer to this question right now and see how many people got it right, since the answer key was wrong on the sheet that you did last night. The answer is D. How many people got that? Good. Good. The new unstable nucleus is at rest when it decays, and the recoil speed of the final stable nucleus is what? I love this question. We see as we go through these 2 practice question sets that you had last night, a couple of questions that you've got to go back and do some older stuff for, including this one. If we have a bomb sitting on a table that explodes, or we had a question, I think, where we had a fireworks sitting on a table and exploding into 3 pieces. We would do conservation of momentum. Well, if we have a nucleus that's sitting there waiting to explode or decay, well, why wouldn't that be conservation of momentum? So just because we're not doing like exploding cars and colliding cars and bombs and whatever, doesn't mean we can't use momentum. If one object becomes 2, then that's conservation of momentum. So we're going to say Pi is equal to Pf for this one. The initial momentum would be 0 because it's at rest when it decays, equals m1 v1 f plus m2 v2 f. m1, we're going to say that we know that a neutron is released here, so we're going to say that mass 1 is the mass of the neutron, 1.67 times 10 to the minus 27 kilograms, times the velocity of the neutron. They give me the velocity of the neutron here, 2.18 times 10 to the 7 meters per second. Now, they also give me the mass of the new nucleus, right? The nucleus, the daughter nucleus. They give me that as 1.99 times 10 to the 26, 10 to the negative 26. And then we solve for VF. And we solve for VF, we're going to get 1.83 times 10 to the 6 meters per second. And clearly we use the law of conservation of momentum. So the answer is D for that one. Does that make sense? Does that make sense? Most importantly, why we do conservation of momentum? Like we're not limited to use conservation of momentum when we have something big colliding or exploding like we typically did back in Unit 1. Now that we know stuff about nuclear decay, we can use that now, as long as something is splitting up. Next one, number 3. Gamma radiation is chosen for food irradiation because, what do we know about gamma radiation? Is it safe? No. Is it low energy? No, definitely not. Is it the easiest form of radiation to produce? Definitely not. What would the easiest way be, the easiest one to produce be, probably? Well, if we're talking about, oh, I see, yeah, okay. Yeah, I was thinking differently. I was thinking a lot about the spectrum, the EM spectrum, okay? Yeah, like when we're talking about radioactivity, we wouldn't say typically the easiest one to produce, because that's a natural process, right? And when we talk about the electromagnetic spectrum, that's what I was referring to. Which one would probably be the easiest one to produce? Probably radio waves, yeah, because it's just oscillating electric charge, and it's pretty easy to do that. Now, we said that radioactivity is a natural process that we can't cause. Gamma radiation, that's a little bit different. We can produce gamma radiation, but not directly. It's produced as a byproduct of something else. So if we have something that will undergo, say, beta decay, then we would expect alpha decay to occur. So we want to make gamma rays. Well, let's get something that will decay via beta decay or whatever, and then we will get gamma rays. So we're not directly causing gamma rays to be produced, but indirectly causing it. Nevertheless, it's not easy to produce. Okay, it's not easy to produce. Does it penetrate into the food through its packaging? Gamma rays have the highest of the 3 types of radioactivity, the highest penetrating power. So that looks like it might work for us. Poses no danger. No, definitely not. It does pose danger to it. All right, next question. So the answer is C for that one, of course. Next question. Recently, I'm not sure what year this was, but this is an old question, so it's not so recent anymore. These people of Oxford University predicted that the decay of radium-223 would emit alpha particles, as well as a few double alpha. You ever heard of a double alpha? No, we haven't talked about that, right? Remember what we said, though, right? You always learn it, or they'll explain it, right? They're telling you what a double alpha is, right? They're not expecting you to just know what a double alpha is. In fact, they're telling us what an alpha is. And we clearly know that. Even some triple alphas here. By the way, how do we know how many protons in the alpha? Well, we probably just know that, right? It's 2. How do we know how many protons in the double alpha? Yeah, we're told that a double alpha is beryllium, and we find that that's 4. And triple alpha carbon, we know that that's going to be 6. The experiment was run for 600 days. The results of the experiment showed the detection of this many alpha particles, but double and triple alphas were not detected. So we predicted we're going to see alpha, doubles, and triples, but we really only saw alphas. 19 carbon-14 nuclei were detected here. Which of the following initial products was observed in the greatest abundance? Okay, so if we take your radium-223, radium has an atomic number of 88, I think. Yep, 88. How do we know what we're going to get in the most abundance here? Like what daughter nucleus? Yeah, go ahead. Yes. Yeah, yeah, okay. I think you're going a little bit too deep into that. Bottom line is we expect alpha, doubles, and triples. What do we get? Alphas. So let's figure out what's left after an alpha particle is released. 4 plus 219 gives me 223. 2 plus 86 gives me 88, and that would be radon. So if the majority of what we see produced after the fact is alpha particles, well then what must be the most common product or the most common daughter nucleus produced? It would be radon 219. Does that make sense? Is that okay, guys? Which of the following products was not predicted by Rose and Jones? It's not going to be 219. Okay, that was predicted because if we release alpha particles, then we're going to get radon 219. Well, they also predicted that we would get double alpha particles. Oops, that's beryllium, right? Well, what's that going to be? 8 plus 215, 2 plus 86. No, sorry, that should be a 4, shouldn't it? And that's going to be, what is 84? Polonium? Okay, well, since they predicted these double alphas, then they would have predicted polonium 215 would have produced as well. They predicted triple alphas. 12 plus 211, 6 plus 82, that's lead, I think. Lead 211. So they would have predicted lead 211 would have been produced as well. So which of the following was not predicted by them? Lead 209, D. Does that make sense? Stop me if it doesn't, right? We got a quiz on this stuff tomorrow, and we got to make sure that we're good with it. We don't want to just say, oh, yeah, okay, he's going over it, it's fine, whatever. Like, well, if you don't understand it, it's not fine. There's not much point in going over it if you're just going to sit there and not get it. Next one, number 6. Talks about a transmutation reaction. Say 12, nitrogen 12 plus an alpha particle. Alpha particle is 4, 2, right? Produces an unstable nucleus. 12 plus 4 is 16. 7 plus 2 is 9. That's going to be, what's 9? Fluorine. Is that just F? Okay. Proton would be 1, 1. And then this would be 15, 8. Oxygen, right? 1 plus 15 is 16. 1 plus 8 is 9. What do we want to know here? We want to know AZ. So that would be 15 and 8. Does that make sense? Oh, look at that. I messed up when I did my answer key here. I did not read the question and answer the question. I said A, 16, 9, because I just went 12 plus 4 is 16, 7 plus 2 is 9, and I just circled 16, 9 without looking carefully enough at it. So we can all mess up like that, right? Not reading the question, answering the question. But I'll tell you what, you think like, it's just a practice question, so it doesn't really matter that I didn't pay that much attention to it. The danger of thinking like that, and we all do sometimes, right? But the danger of thinking like that is we get in certain habits, right? We get in habits of, we either get into good habits or we get into bad habits, and good habits are better than bad habits. So you should try to build good habits. Next one, 3 questions, talks about this Mars Pathfinder mission. And then it's got some information that, of course, you're going to read, you're going to skim through, and then you're going to read the question and look at it in more detail. It says in the nuclear reaction here, question number 1 says, in the nuclear reaction above, what are the values of A, B, C, and D? That should be pretty straightforward to us. We say 4 plus 23 is 27, 1 plus 26 is 27. 2 plus 11 is 13, 1 plus 12 is 13. So my numbers A, B, C, and D would be 2, 6, 1, 12. In the nuclear reaction equation above, element X is what? Element X is, well, we're looking for atomic number 12, and we just look on our periodic table for that. We find it, atomic number 12, we find that it's magnesium. Careful, don't say, what should they have put there as an option? What should they have put there as an option? Why carbon? Why should they have put carbon as an option? It would be wrong, but why should they have put that as an option? Yeah, that wasn't what I was thinking, but yeah, you look in your periodic table, the mass of carbon, the atomic mass of carbon is 12.01, right? Okay, remember what I said though, you never use that bigger number. You'll never use that bigger number in physics 30. Chemistry will, but not in physics. Okay, 2, when the signals were sent to Sojourner, the distance between Earth and Mars expressed in scientific notation was what? This is a question from last unit. It's just in the context of this stuff. We're just going to say V equals D over T. D is equal to V times T. V is 3 times 10 to the 8. And the time it said was 10 minutes, which is 600 seconds. And when we do the math, it's 1.8 times 10 to the 11 meters, or we'd express that as 1811 meters.